Our today's topic of discussion is cytoskeleton. Now, we know that in our body, bone is the main structure that maintains the strength and stability of the body. Similarly, the cell also has a structure called the cytoskeleton. Now, by definition, cytoskeleton is a system of fibers that help in maintaining the cell shape and form, and also it helps in changing the shape of the cell and also in the motility of the cell. So, there are three main functions. It maintains the cell shape, permits to change the shape, and also helps in movement. There are three components which contribute to the cytoskeleton. These are the microtubules, the microfilaments, and the intermediate filaments. Okay, these are the microtubules, microfilaments, and the intermediate filaments. Now, let's have a quick comparison of these two. We'll understand why they are classified differently. To start off, microtubules are the biggest ones over here. These are the big filaments compared to the three of the structures. So, the microtubules are big filaments and measure about 25 nanometers. And you have to remember the three important types of microtubules, highly important all of them. These are the Tubulins for tubules, Kinesin, and Dynein, right? Tubulins, Kinesin, and Dynein. Now the second one is microfilaments. These measure up to 7 to 9.5 nanometers. The important one is actin. And another one you can guess, actin is always paired with myosin. These are microfilaments. And the intermediate filaments, these are the most abundant type of filaments. They measure 10 to 12 nanometers in size, and the various types of intermediate filaments are Lamins, Keratins, Vimentin, Desmin, Neurofilaments, and GFA. Now let's look in detail about the microtubules. We have seen that there are three main types of proteins constituting the microtubules. These are kinesin, dynein, and tubulin. So the tubulin, as the name suggests, these are fine hollow tubules, and it has two globular structures, that is alpha and beta tubulin, which are heterodimers, right? Now you can see in this image the structure of microtubules. It essentially has a helical structure with a protofilament that is marked here along with its tubulin units, right? The alpha-tubulin and the beta-tubulin, which are the heterodimers, right? You do not have to remember all this. This is just for information I am sharing with you. Okay. Now the main property of microtubules is that these are polar and in a state of dynamic instability. Okay. These are polar and usually in a state of dynamic instability. Now what you have to remember for the exam is the functions. You'll have to memorize all of them. We'll try to remember them easily. So the first and the most important function is they form the structural component of cilia and flagella that are present in various cells of the body. Okay. They also form a major component of axons and dendrites, thus maintaining the neuronal structure. Now, here the microtubules are very important for one concept that is called the axonal transport. Right? We will understand what is axonal transport. So, they have an important role in playing the axoplasmic transport. Before we understand what is that, just see that there are two types based on their speed. It can be fast, where it moves about 400 millimeters per day, or slow, where it moves about 0.5 to 10 millimeters per day only. Okay, now look at this structure over here. Okay, this is the cell body of the axon of the nerve cell. This is the axon, and okay, this is the nucleus. This is the synapse. Okay, now the various substances that are synthesized within the cell body, they move through the axon and are stored in the synapse where they are released. We are familiar with this concept. So, when the substances are moving from the cell body to the synapse, this movement is called forward axonal transport, and this is facilitated by our kinesin, the microtubular protein, that is kinesin. Movement of substances from cell body to synapse, that is forward axonal transport, is facilitated by kinesin, and the reverse of this reverse transport is facilitated by Dynein. Kindly remember these two, these are important questions. Forward axonal transport kinesin, reverse axonal transport is Dynein, right? Another function is it determines the shape of the cell and also gives us structural support. And because it is present in flagella and cilia, you can understand that it helps in various types of cellular movements that can be intracellular movements, cell locomotion, secretory granular activities. Yeah, we'll look at them in detail. Another important function is they are necessary for formation and functioning of mitotic spindle, right, in cell division. In cell division, they are important for formation of the mitotic spindle. And also one more point, in cell division, they are responsible for the chromosomal movement during cell division. Here, your tubulin is important. A tubulin helps in improving the chromosomal movement and encourages cell division. So the applied physiology over here is when you inhibit the tubulin, you can easily understand that cell division is stopped. So when there is no cell division, the cell will die. So this concept is used in anti-cancer drugs such as vinca alkaloids and taxanes. These are classified as microtubule inhibitors, thus inhibiting cell division and promoting cell death of the cancer cells, right? Now, the mechanism by which rabies virus, polio virus, herpes virus and also tetanus toxin travel through the nerve cell is facilitated by microtubule. Rabies, polio, herpes and tetanus toxide, they traverse by the reverse axonal transport mechanism, which is again supported by Dynein. Okay. Now, let's look at the functions of Dynein in detail. The most important one over here is movement of sperm and fallopian tube. You know that the sperm must reach the fallopian tube for fertilization. This movement of the sperm is facilitated by Dynein, and it also helps in ciliary development. Now the applied part over here, during the developmental stage of the fetus, if this ciliary development doesn't occur properly, the internal rotation of the organs is disturbed. Okay. Now, another important function is clearing of sputum in the lungs, which is of protective action for the lungs. We have just seen that when there is a disturbance in the ciliary development, there is a malrotation of the internal organs, right? This condition is called Cartagener's syndrome or immotile cilia syndrome. Occurs due to absent Dynein, and it is characterized by sinusitis, bronchiectasis and situs inversus. See, both of these functions are disturbed. So, with respect to sputum, there are two features in the triad, sinusitis and bronchiectasis in the lungs, and for the internal organs, there is situs inversus. So, this is the classic triad of Cartagener's syndrome. An associated feature is infertility because the sperms are also immotile, right? Because of Dynein abnormality. There is a condition called asthenospermia. This is not a part of the triad, but a patient of Cartagener's syndrome is usually infertile, right? So that is the importance of Dynein. Now let's look at microfilaments. These are small size filaments right? And the important ones are actin and myosin. So these actin and myosin structurally are coiled helically. Okay, you can see here the helical structure of the microfilaments, and the most abundant type of microfilament is actin. About 15% of total protein is constituted by actin. It is present abundantly in lamellipodia and in the microvilli core of the intestinal mucosal epithelial cells, right? The function, the main function, whenever you remember actin and myosin, you will remember skeletal muscle. So the function is contraction of skeletal muscle. That is, we know this famous theory, the sliding filament theory. Okay. Now, another concept over here, the actin polymerization also helps in cell motility, right? So another function apart from muscular contraction is cell motility, especially that of actin, and this is seen in Listeria monocytogenes, right? With the help of the polymerized actin tail, it has a tumbling motility. So the motility of Listeria monocytogenes is given by actin, polymerized actin tail. Now let's quickly look at intermediate filaments. These are elongated fibrous molecules with central rod domain, an amino acid terminal head and a carboxy terminal tail. You don't have to remember their composition. But the important point that you will have to remember is they are most abundant type of cytoskeletal filaments, and these are very stable structures, and they also act as tumor markers, right? So the tumor markers are nothing but your intermediate filaments. We will see which type indicates which tumor, right? Before that, there are certain classes of intermediate filaments. Class 1 is lamins, present in the nuclear lamina, keratins, present in the epithelial cells, hair and the nails as the name suggests. Then Vimentin-like intermediate filaments have three types, that is Vimentin, present in the connective tissue, that is fibroblasts, Desmin, present only in the muscles, and GFA, that is glial fibrillary acid protein, that is present in the glial cells as the name suggests, especially in astrocytes, right? So Vimentin is present in fibroblasts, Desmin is present in the muscles, and GFA is present in astrocytes. Now the fourth class is neurofilaments, and they are present in the neurons. We have seen that these are important tumor markers. So let's look at them. Now keratin is a marker for epithelial cell tumor. The marker is cytokeratin. Especially for squamous cell carcinoma, you will be using this cytokeratin as the marker. Now Desmin is an indicator for sarcoma, especially rhabdomyosarcoma. Then Vimentin for any tumors of mesenchymal origin. Then GFA for astrocytoma or glioma. See, all of these indicate tumors of where they are present. Okay. Now lamin is a mutation of lamin, causes premature aging or progeria. This is an important question. So the mutation of lamin causes premature aging. This condition we call as progeria, and the syndrome is called Werner's syndrome. Okay, let's just revise all these points. So keratin is present in epithelium. We are familiar with that. So wherever there is squamous cell carcinoma, cytokeratin is your marker, right? Now Desmin, we have seen that it is present in the muscles. So any sarcoma, the marker is Desmin, especially rhabdomyosarcoma. Now Vimentin is present in fibroblasts. We have seen that. So any tumor of mesenchymal origin is Vimentin. Then glial fibrillary acidic protein, as the name suggests, glial tissue. Most importantly, astrocytoma, then glioma, right? With respect to lamin, any problem with lamin, that is mutation,